Good afternoon. Welcome to the UC Davis TERC Summer Science Speakers Series. My name is Jeff Schlatter. It's my honor to serve as the director of TERC. Today's presentation is part of our broader education programming, seeking to engage with both the Tahoe and the non-Tahoe public. I wanted to acknowledge the financial support of many people in the community who support our public education, outreach, and research efforts. They would not exist to the same extent without you. If you would like to support these efforts, please visit our website, tahoe.ucdavis.edu. Coincidentally, and thankfully, a large part of what today's presentation touches on was initiated by gifts, both large and small, from individuals such as yourselves. Without that independent funding to launch our studies on the Mysis in 2011, the new knowledge gained and the new possibilities that were opened up in the last 10 years would not exist. So before I introduce our speaker, just a couple of housekeeping items. First, if you have questions, please use the Q&A button. Don't shout at your computer. Don't use the chat button. Brant Allen will try to answer most questions today, and if not, we will get back to you by email. We're also compiling a frequently asked questions section on our website. Secondly, if you need to leave early or want to share today's presentation with your friends, it is being recorded and that will be available for viewing from our website as well. So now, to Brant Allen. So Brant Allen has served as TERC's field director, primary boat captain, and limnology researcher since 2004. As such, he has borne the responsibility for the safe conduct of all our operations on the lake, under the lake, and in remote sites. And these are operations not just taken by our staff, but by students, by summer interns, even by faculty. And that's a lot of responsibility. Our operations take place year-round. They take place day and night, as you'll hear about later today. And over this period, his safety record has been perfect. In addition to all the other things he has done, Brant is the eyes, has the eyes of Lake Tahoe. He is the one that most times goes out and takes the Secchi depth measurements up to 25 times a year. It's a responsibility he took over from Bob Richards in 2004. So Brant was initially hired for a 2-month project as a fisheries ecologist in 1990. And somehow through his skills, dedication, and possibly flying below the radar, he stayed on for the intervening years. So 1990 to the present, that's 30 years. So I guess I have a little award here that I'm going to make virtually to Brant. I'm not sure how best to do this. I'm not sure if you can see this on Zoom. Oops. But this is a pin. This is a pin I'm presenting on behalf of Helene Dillard, Dean of the College of Agricultural and Environmental Sciences. And it's being presented to Brant to commemorate his 30 years of service to the university. The pin has what appears to be 4 blue objects embedded. I can only presume they are sapphires, as it comes from the University of California. So anyway, Brant, on behalf of not just TERC, but the entire university, thank you for your 30 years of service. So at this point, I'm going to hand the presentation over to Brant. As usual, these things can be a little bit klutzy. So we're going to give it our best shot, and Brant's going to take over at this point.
All right. Thank you, Jeff, for For the award, I will look forward to having you pin that on my lapel when we were in the same room. Thank you all for joining the talk today. I am going to be talking about Mysis shrimp in Tahoe and how they have affected the food web in Tahoe, and it's trawling for transparency. So how native food web restoration could actually help achieve Tahoe's clarity goals. This project was made possible through funding by the California Tahoe Conservancy and the Nevada Department of Environmental Protection, and we greatly appreciate their continued support of research at Lake Tahoe. There are a lot of people that made this project possible, and I'm going to point out some of them here, just to know there's a lot of names I'm not going to get to in this slide. But I wanted to thank Kevin Boswell at Florida International University. He provided the trawl that we initially used in this project. And Dan Shaw with California State Parks worked on logistical support so that we could maintain our research vessel down in Emerald Bay and made a much more efficient project for us. Zach Bess and Siddhi Chandra at University of Nevada, Reno were collaborators on this project, and they worked on in-lake feeding experiments that were critical to understanding how the whole food web was working. There were a lot of people behind the scenes, writing the reports, doing data analysis, and when you work with the whole food web, you have experts, fortunately at UC Davis and in our group, that really know all the details of each different aspect of it, from instrumentation and programming down to measuring the phytoplankton and zooplankton. So a great appreciation to all of those that helped out. And finally, thank you to the nocturnal field crew. You all know who you are. But more importantly, maybe thank you to the significant others that put up with as best they could with the crazy night hours that we all had out there on the lake. So I'm going to run through a bit of history to bring us all onto the same page, and then move through our understanding of Mysis at Tahoe and talk about this project. So I'm starting with ancient history, and ancient history runs from 1949 to 1987. And during ancient history, there was this idea that we could use introduced species to improve upon Mother Nature. And after about 1970, we started to understand that maybe some of those efforts weren't in our best interest. And it was realization that some of these things actually had repercussions that we weren't anticipating. So let's start with what is a Mysis shrimp. It was previously known as Mysis relicta. Now it's Mysis diluviana. So if any of you are geeky people that like to go back and review scientific literature, if you are seeing that all the Mysis is referred to as relicta, we're still talking about the same species. It's a freshwater shrimp that's about 1/2 to 3/4 of an inch in length. They're very competent swimmers. They're sensitive to light. You can see that in the image. They have very big eyes. So they do a vertical migration every day away from light. So during the daytime, they're down at depth. At night, when it gets dark, they come up back to the surface again. Mysis like cold water. They're native to the Great Lakes. They're omnivorous predators. So they'll happily feed on detritus matter on the bottom. They'll feed on algae, phytoplankton in the water column. And they'll also feed on zooplankton and selectively feed on Daphnia, which will come up. So Mysis were first introduced in 1949 in Kootenay Lake in British Columbia. And they came from the Great Lakes. And the study in Kootenay Lake, they were put in to try and enhance the forage base for game fish. And in Kootenay, for better or for worse, it actually worked, at least where the study site was. So the study site was in a relatively shallow bay in the lake. And while the Mysis did their vertical daily migration, the bay was shallow enough that Kokanee salmon that were living in the lake could actually feed on the Mysis during the daytime. And so the Mysis couldn't escape the predation, and the kokanee got very large as a result. Well, this was viewed as a great success, and with other lakes and fish and game departments looking to enhance recreational opportunities, Mysis were deposited in 134 lakes across the western United States. Tahoe was one of those lakes, and it received its Mysis in 2 different batches in 1963 and 1965. And the important thing there is that while they were put in the mid-60s, the Mysis didn't become fully established in the lake until about 1971. Well, following those introductions, we started to do these studies, and there's some fantastic researchers at UC Davis that really did this period of understanding how the Mysids lived in Lake Tahoe and how they affected the food chain in Lake Tahoe. And those studies really formed the basis for a lot of our knowledge today on what changes occurred. But it's interesting that keep in mind that these studies were done during a time period when Tahoe's primary productivity was about a quarter of what it is today. So the algal growth rate in Tahoe back in the 70s has changed dramatically. So as the shrimp were in the lake, Tahoe continued to change long after they became established. All right, we've gotten through ancient history. We're going to go into modern history now, the age of discovery. Modern history takes place from 2011 through 2016. And we had a postdoctoral student, Allison Gamble, came out from doing her doctorate work in the Great Lakes on Mysis. And at Tahoe, she was curious that there hadn't been a really detailed Mysid study since the early 1980s. And so she wanted to look at what changes might have occurred in the Mysis population and if there was something there that we should be looking at. So we picked some study sites, and one of them was in Emerald Bay. We went into Emerald Bay in 2011, and we found that the Mysis had virtually disappeared. There was 0 to 1 Mysid per meter squared, and typical numbers would be more like 80 to 100 per meter squared. At the same time, in Lake Tahoe, the Mysids population was exceptionally high. There was roughly 400 individual Mysids per meter squared. And typical in Tahoe would be more like 100 to 130 Mysids per meter squared. So in Emerald Bay, with the disappearance of the Mysis, and we don't know why they disappeared, but when they disappeared, we saw this rebound of native zooplankton and specifically Daphnia. So when the Daphnia came back, they're very good grazers on fine particles and small algae cells. And within 18 months, the water clarity in Emerald Bay doubled. It went from 12 meters to 24 meters. And it was the first time we had recorded Emerald Bay water clarity exceeding that of Lake Tahoe. By 2016, the Mysids had come back. And as their population grew, the Daphnia population slowly disappeared because of predation by the Mysids. And as that happened, the clarity went back to 12 meters. So seeing this whole process work out over 6 years, it really raised the question, could we physically remove Mysis from Emerald Bay and generate the same kind of lake response that we saw during that time period? So this is just a graphical representation of what I just said, but the top portion of the graph is the clarity measured by Secchi depth, and the bottom is the zooplankton and Mysis abundance. And so if you look at the left on the bottom, you see that the red bars don't exist. Those are the Mysis. That's when we showed up, and the Mysis were gone. We had the rebound and appearance of Daphnia, and it correlated beautifully with this dramatic clearing of the water column up above. And then as you move to the right across the bottom graph, you see that the red bars start showing up. Those are the Mysis coming back in. And what we found was that when the Mysis population reaches a density of 27 individuals per meter squared, greater than that the Daphnia can no longer coexist with the Mysis. And so what happened is you see the red bars get more consistently thick and the Daphnia disappear, the blue bar at the bottom, and essentially the water clarity goes back to what it was. Okay, so now we're in the current times and we are in search of a cure. So this is the project that I'm going to spend the time talking about. Just got through the background for why we did this. The project took place from 2018 through 2019. And there were really 4 primary goals. The first was to gain a detailed understanding of the life history of Mysis in Emerald Bay, focusing on how that life cycle could enhance our removal efficiencies. The second was to develop acoustic survey techniques for assessing Mysis density with an application that same technique would be applicable to be used in Lake Tahoe. We also then wanted to physically reduce the Mysis abundance, trying to get it down to that 27 individuals per meter squared. And we would do this through physical trawling, just actual removal of the shrimp from Emerald Bay. If we got it down low enough, we hope to see the same response of Daphnia returning to the bay. And the fourth one was the work that was done by UNR doing the feeding experiments. They did in situ experiments, so enclosures in the lake where they took different segments of the food web and looked at the interactions in great detail and how it affected water chemistry and phytoplankton within these incubation containers. I'm not going to go into their work in detail. It is contained in our report, so I do recommend that you read those sections in the report because there's great value information in there. Okay, the life history of Mysis in Emerald Bay and Tahoe. So it's interesting, Emerald Bay Mysis have really a 1-year life cycle, a 1+ year life cycle. And this makes their population very vulnerable to any kind of change. So we don't know what happened in 2011 or prior when they disappeared, but with a 1-year life cycle, if you think about it that way, all of the adults that are out in the bay have to reproduce themselves in 1 year. And if anything were to go wrong with the following year class, your population is going to go through a crash. Tahoe Mysis in Tahoe, or Mysis in Tahoe, have a 3 to 4 year life cycle. Interestingly, between the two systems, or in the two systems, the timing of the life cycle is the same. So the release of juveniles and the timing of reproduction is taking place at the same time in Tahoe as it is in Emerald Bay. So why do these two populations have this very dramatically different life cycle timing-wise? And it's really driven by energetics. So the Mysis in Emerald Bay, when they do their vertical migration, they go down 60 meters and they get to the bottom. During the daytime, they can actually feed on the detritus that lands on the surface sediments there. And then at night, they can go up and feed on phytoplankton and zooplankton. In Tahoe, the Mysis, for the most part, are making a 300-meter migration one direction. And unless they happen to land in the fringe of the lake where they end up on the bottom, the bulk of the population is going to remain pelagic out at 300 meters. So when they drop down into darkness 300 meters deep, they're not on the bottom. And there's just a lot less feeding opportunities there. So the combination of having a much greater swim and a diminished daytime feeding opportunities in Tahoe makes it so that the Mysis there take 3 to 4 years to reach maturity, whereas Emerald Bay, they can do, the bulk of the population can reach that state in 1 year. So we're going to look at the detail of the Emerald Bay life cycle. I'll start at the top in winter, where we have pregnant females. They're generally 16 to 20 millimeters long, and they are carrying eggs and the developing embryos in a brood pouch. And these embryos basically grow up through several different stages, and when they're ready for release, the females release the juveniles into the water column, and the females die. So that takes place in late winter or spring. And so in spring, we have an abundance of the new year class of juveniles, and these are 5 to 10 millimeters in length. And they selectively seek the nearshore areas. They're less vulnerable to light, so they can live a little bit shallower. And they seek refuge there from fish predators, but also from any cannibalism by adult mysis that did not breed in the past year. So as those juveniles start to grow in summertime, once they get to about 12 millimeters in length, they start moving pelagically again. They start moving away from shore and out into the center of the bay. And then by late summer, fall, reproduction takes place. So those shrimp that are greater than 15 millimeters, they reproduce. The males die after reproduction. The females carry their eggs into winter, and we're back to where they go through the stages of development. So this is images of the developmental stages of mysis prior to the release. So these were extracted from the brood pouches of captured females and photographed under the microscope. And on the top left, what you see are eggs. And then right below that, stage 1. Middle panel, you see stage 2 and 3 of development. And you'll notice that stage 4 is missing. That's because the transition from stage 3 to stage 4 takes place very quickly. So we were not able to capture photographic images of stage 4 life cycle. And on the bottom right, you have stage 6 of mysis development. This is what they look like right before they're released out into the water column. So we had this understanding now of the life cycle, and from our netting, an idea of where each stage of development actually existed in Emerald Bay. But what we wanted to be able to do was to map these densities rather than taking single net tows from the bottom up to the surface and counting the mysids. We wanted to validate what was going on throughout the entire area of the bay. So we used a Biosonics split beam echo sounder, and it's basically a very fancy fish finder. And what we needed to do first was to validate the targets. So we used the echo sounder at the same time that we were doing vertical net tows. And we could line up the exact signal return on the depth sounder with a known number of mysids in the water column. That helped immediately for knowing whether what we were seeing were mysids. But then we had to refine the mysid targets and eliminate them from the fish targets, the bottom echoes, and noise in the water column. So a program was written to do this, and eliminating fish targets is relatively easy. Fish have a swim bladder, and even small fish have a much higher return signal than a mysis does. So if you look in that image on the bottom and the right, you can see some fish targets that are in there. Separating those out from mysis wasn't too difficult. The bottom echoes also weren't that difficult. The bottom tends to return a similar echo all the time, and it doesn't change depth readily in the center of Emerald Bay. So that was pretty easy to screen. The noise issues were a little trickier. During the summer, when you have lake stratification, the thermocline, where the water temperature changes dramatically from warm to cold as you go deeper over a short distance, you can get a echo return off of the thermocline. And it's a pretty weak echo return. So separating that out from mysis signals was pretty tricky. So what we ended up doing was looking at mysis return signals below the thermocline and setting the thermocline as the upper boundary of our mapping densities. And this really isn't a problem because, as I said earlier, Mysis are cold water specialists. So they don't want to venture through the thermocline up into the warm waters. In fact, this year and in previous years, we've seen now that Tahoe's summertime surface temperatures above the thermocline are actually lethal to Mysis. The last problem was, how deep could we see the Mysis? So when a Mysis, imagine it's a pretty small return signal acoustically off of a Mysid, and by the time you get down to about 150 meters, just the background noise of the instruments merge with the Mysid signals. So we used 150 meters as the bottom depth for looking at Mysis detections. Now, this really wasn't a problem either because we're looking at Mysids when at night with the echo sounder to map their densities, and they are up above 150 meters during that time. They come up much shallower than that. So we felt pretty comfortable with reliably detecting the Mysid densities using the thermocline as an upper barrier and 150 meters as a lower depth range. So once we had that figured out, we looked at the daily vertical migration of the shrimp. And we did this in two different ways. In Emerald Bay, we attached the echo sounder to the research vessel and moored the research vessel over the deepest part of the bay. In Tahoe, we attached it to one of our deep water buoys. And in both cases, we let the instrument run for 24 hours. And what we were able to see was that the Mysis came up as expected off the bottom, and their ascent rate was just under a meter per minute, 2.9 feet per minute, and their descent rate was calculated at 2.7 feet per minute. So this provided some important information to us. First, in Emerald Bay, the Mysis can make their migration from the bottom up to the shallow water in 1 hour, and the return back in just over an hour. So this confirms that Mysis in Emerald Bay are actually able to spend the daytime on the bottom of the bay, anywhere in the bay, and have that advantage of feeding. It also told us that if we wanted to do our surveys for density, but also our trawling efforts, we needed to wait until an hour after dark so that the Mysids had the ability to get up to their shallowest depth zone, concentrating themselves in that shallow band where we'd be more efficient in our trawling efforts. It also pointed out that in Tahoe, with a descent rate of 2.7 feet per minute, in the deepest part of the lake, it would take 9 hours for Mysids to transit from the surface down to the bottom. Again, that's a one-way ticket, so you got to come back. So 18 hours of transit time, and it's just very unlikely that Mysis are actually going all the way to the bottom of the lake in Tahoe and back again. They're hanging out somewhere in that depth zone in the middle pelagically. So with the vertical, able to distinguish the vertical distribution, we moved on to the horizontal spatial distribution of Mysis. And to do this in Emerald Bay, we picked 20 survey lines through the bay that were repeated, the exact same lines were repeated, integrated between transect lines so we could create a spatial map. So this is what the spatial maps look like. Warmer colors being higher densities of Mysids, cooler colors being fewer. And we were really pleased with these because they actually mimic what we were seeing with our net tows. So if you look at March on the top left, you see that it's springtime and the higher densities of Mysids are around the shoreline and the nearshore areas. That's our new year class of juveniles. In June, it gets a little more patchy. And the start of summertime, we're starting to see this movement of Mysids out toward the pelagic zone. And by August, in the right panel, you see that the bulk of the Mysid population is out in the pelagic zone of Emerald Bay. So we translated this same survey technique to Tahoe. And if you look at that bottom right panel, you see that there is a survey line there, but it's a very small area of Lake Tahoe that was covered. So in the amount of time it takes to do the entire bay of Emerald Bay, we could really only go from the Tahoe City Shelf to Dead Man Point and back. So what this told us was the survey techniques using the bioacoustics is very good, but it's going to have to end up being done autonomously, or at least partially autonomously, because the amount of time, effort, and manpower to do a broad scope survey of Tahoe would just take too much time and too much manpower. So now we had density maps showing us where the mysids were, and we knew what stage in the life cycle where they were when they were in different parts of the bay. So now we just needed a net in order to catch them. And trawls really come for mysis in two sizes. You can get extra smalls and extra larges. Extra smalls are basically designed for research trawling, taking samples, so about a square meter. And there was no way that that was going to effectively harvest the shrimp population out of the bay. The extra large trawls are so big that our research vessel would not have been able to tow them. And custom nets are available, but they are prohibitively expensive for a pilot study. So what we were able to do was reach out to the research community, and we borrowed an Alouette midwater trawl from Florida International University. They graciously shipped it out to us so we could use it for the project. And it was fairly large. It had an opening of 56 square meters, but the mesh was pretty coarse. It was designed for marine mysis, and the back end of the trawl, the cod end, had a mesh of about 2 millimeters, which was pretty good. But the front end allowed too many mysids basically to just go through the mesh of the net. So using this trawl, we learned how to pull it through the water. We learned how to operate the boat. We refined our efficiency, but we really needed to catch more fish, or sorry, more mysis as we were out trawling. So we made a series of net modifications. And our first effort, we took 6 millimeter mesh and we sewed a sleeve inside the original trawl. So in the left panel, you see the original trawl in dark green, and we sewed this white mesh, reducing the mesh size. And we were able to catch more shrimp with that, but the drag became so great, it was almost like pulling 2 trawls through the water. So our boat speed dropped below a knot, and we were unable to make a U-turn within the confines of Emerald Bay. So we had to set the trawl out, do one length of the pelagic area of Emerald Bay, pull the trawl back in, turn the boat around, put the trawl back out, and head back the other way. So efficiency-wise, it just wasn't going to work for us. So we decided we would design and make our own trawl, which we did. We had it commercially sewn, but we checked it. We made all of the net dimensions the way we wanted them, and that is the result is the panel on the right. And we built a float line and a lead line designed after the original Alouette trawl, and attached them to ours. And we continued to use the large trawl doors that hold the trawl open to the water as you pull it through with the boat. We used the original materials off of the Alouette trawl. So we ended up with a trawl that was 13 square meters instead of 56. Finer mesh makes it so there is more drag, so we had to reduce that size. And the mesh size started at 6 millimeters and went back to 0.5 millimeters at the back end of the trawl. So the goal was to trawl for maximum harvest. What we really wanted to do was to create population collapse of mysis in Emerald Bay. And to get to about 27 individuals per meter squared, we were looking at a 2/3 reduction in the standing population of mysis. Well, there's really 2 ways to do this, and there's fantastic examples all over the world because just about every commercial fishery has brought its population to collapse. And the way you do that is that you harvest adults before they're able to disperse, they're young, or you harvest the juveniles before they are able to reach maturity and breed. So we started in the fall, winter, and we were looking to harvest the adults, the males before they breed, the females before they release their young, out in the pelagic zone using our large trawl. We were able to catch 3.2 kilograms per hour of shrimp doing this. That was on average. And just so you have a number with that, that's about 62,500 mysis per hour. So a lot of individual mysis were being removed. There are some disadvantages to working in the winter on Tahoe on a metal boat. We experienced temperatures out there down to 10 degrees. And when everything is wet, you're pulling in a wet trawl, the deck gets wet, everything freezes, and at 10 degrees, it pretty much flash freezes. So there's just something to give you a little audio taste of what it's like trawling in the wintertime. So during this time period, when we realized saw what our average catch was going to be, our harvest rates, we calculated based on the abundance of shrimp in Emerald Bay, how long it was going to take to reach our target goal. And we came up with 290 nights. Well, this was a problem for two reasons. One, the nocturnal field crew did not want to spend 290 nights out on Emerald Bay. But really the more important problem was that it didn't fit into the life cycle time frame that we needed. So we had roughly 3 months while the adults were, before the adult females released their broods into the water column. And if it was going to take us 290, we were going to be pulling our trawl through empty water out in the middle of the bay while all the juveniles had gone off to the near shore. So we redesigned how we were going to go about phase 2 of this, collecting the juveniles. And so we switched our trawl system and we used 2 commercially available sampling trawls coupled together into a single custom built frame. Now it gave us, again, a much more reduced trawl size, 1.5 square meter trawl opening. And we were targeting in shallow water. So what we did is we pulled this assembly through the water in depths less than 20 meters around the near shore of Emerald Bay. And we were able to do that with our smaller vessel. So it was more nimble, it was a much easier system to use, but because of the smaller opening, our catch rate went down. We were catching 0.4 kilograms of shrimp per hour. On the bright side, because these juveniles are around 10 millimeters in length, we had 23,000, roughly 500 mysis per hour being caught. So the numbers of individuals were quite high, even though the kilograms catch had dropped dramatically. So what we realized is that we're going to need a bigger boat. We calculated, looking at scaling up, how would you scale this up to a commercial level? And so we looked at just what is really available out there for commercial harvesters. And we looked at trawl size, boat speeds that you could pull those larger trawls at. And really your harvest is proportional to the size of the trawl you're pulling, the speed of the boat, and the hours that you're pulling it through the water. And so we calculated that if it were a commercial operation, we could potentially increase our catch 16-fold. And when we applied that to the mysis population in Emerald Bay, we calculated that you could remove the shrimp to our target values in 20 nights. And that was pretty promising, but this was really based on what's available. So then we looked at a commercial mysis trawling operation that actually exists in Lake Okanagan. And they've been commercially harvesting mysis there to enhance kokanee populations for about 15 years. And they average 300 kilograms per night. But their mysis density is about twice that of Emerald Bay. So if we assumed an average catch of 150 kilograms a night in Emerald Bay, using similar techniques and sizes of trawls and boats and things like that, it would come down to reaching our target goals in 22 nights. And this was pretty promising because it lined up well with just our general calculations of what might be possible. Now, it's important to recognize that the actual time needed to reach that target goal of 27 individuals will go beyond the 22 nights. As your targets, as you get closer, you have fewer mysis in the water column. So your just catch per unit effort is going to go down, extending the time you need to harvest. And then also, of course, any weather constraints and things like that. But it was promising that a verified harvest in a larger lake than we were working on could actually reach our goals in a meaningful time frame. So how would you move a commercial harvest to Tahoe? If you were successful doing it in Emerald Bay, what would you need to know to move this into Tahoe? And there's a couple of things that would be critical. The spatial distribution of mysis, we really don't know that well because all of our historic data is really based on single point vertical net tows from anywhere from 5 to 20 different locations around the lake. But we need to create these density maps where we could greatly increase trawling efficiency if we had these color-coded mysis density maps. So the way to do that is to cover more area, and autonomous vehicles going out on a nightly basis using the same type of biosonic equipment, echo sounding equipment that we used, and using the same programs to determine the mysis densities. They would be able to go out and survey larger areas with a lot less complaint than the staff would, and create these images for different regions of Tahoe. The other thing that would be really important to do is to develop a 3D model for Tahoe's currents. So we have a very good 2D model that shows us how the surface water currents move around the lake. But mysis are really a three-dimensional animal in that they go down to depth during the day. So if we could incorporate a mysis model into the 2D model where you had the idea of the mysis coming up and taking part in that two-dimensional surface movement, but then leaving and going back down to depth during the daytime, do those currents actually concentrate mysids in certain areas? Those are the type of questions that we need to ask. So essentially a mysis model for Tahoe and a way to create these same spatial distribution maps would greatly increase the harvest efficiency when it came time to trawl. Well, assuming you gathered up all these mysis, what do you do with them? And we were very fortunate in this study that the UC Davis Graduate School of Management chose our mysid project to look at the commercial viability of harvested shrimp and coming up with products of what you would do with them. So the first step was to look at the nutritional content of the mysis, and through the Davis Food Lab, it turns out they are very high in omega-3 fatty acids. They're actually 14% higher than wild-caught salmon, which has tremendous food value, and the fact that they come from Lake Tahoe, which is a pristine mountain lake, so you don't have to worry about a lot of the ocean issues that you would with mercury and perhaps endocrine disruptors that you might in other freshwater systems and things like that. And Tahoe is viewed as a very pristine environment for deriving food from. So what they came up with was a premium dog treat viable market made from harvested mysis shrimp. And there are a lot of other products out there. For instance, the Lake Okanagan harvest goes to making shrimp for the aquarium trade. And the nice thing about that is that there's almost no processing. You just freeze the shrimp and they're ready to go to market. The other option is that you could go with more of the krill oil or the omega-3 extract for the high-end market of pharmaceuticals and supplements. The problem with that is that bringing that to market takes a great deal of time. There's a lot of hoops you need to jump through before you can bring one of those products to market. So the premium dog treat actually came out as a quick, limited processing and highly valuable market for the shrimp. And we really got excited about this when they started doing these presentations. The graduate school students did a fantastic job. And we were almost as excited as this dog was getting his treat. But then when they said, you could make this potentially sustainable environmental restoration, that made it even better. So the model design is that you create these premium dog treats, you sell them, and the revenue generated goes back into the environmental restoration. And as projects get harder and harder to fund, environmental projects specifically, especially projects that take longer periods of time, we're not going to clear Mysis out of Tahoe in 1 year. And so if you have to continually go back and look for new funding to get a extended restoration project completed, having a sustainable option is really fantastic and exciting. And I think this goes way beyond just the Tahoe Basin. Putting this out as a sustainable option for other systems is really exciting. So now I'm going to talk about the future, 2021 and beyond. What happens in Tahoe with a diminished Mysis abundance and potentially a robust return of Daphnia population? Well, this is how we conceptually view the food web, from lake trout through Mysis and Kokanee down to Daphnia in the center, fine particles of Cyclotella affecting clarity. And what we really focused on mostly is this section right here. So we predict that clarity would improve with a reduced Mysis population and Daphnia coming back. Daphnia are excellent grazers on small algal cells, and I'm going to specifically call out Cyclotella and inorganic fine particles. So as they graze on fine Cyclotella and fine particles, those are the primary drivers in Tahoe's clarity loss. And Daphnia are very good at filtering that exact size particle out of the water as they feed. The clarity loss in Tahoe has been, the summer clarity loss has actually been more pronounced than winter. And the nice thing about Daphnia is that Daphnia are warm water tolerant. So when you have a stratified lake and you have this warm water sitting up above, the Daphnia can use that warm water and feed on fine particles and Cyclotella. And that is the exact depth that is most critical to Secchi depth change. So we see Daphnia as having a great ability to improve clarity in Tahoe. But there is some scientific debate about this. How dramatic a change would you see if Daphnia came back in Lake Tahoe? There's been papers published on saying that the lakes with very low primary productivity, so lakes that have very little algal growth in them, don't see much of an effect of a top down, so a zooplankton grazing down on algal effect. It's more of a bottom up effect that they see in those lakes. So when we try to compare Emerald Bay and Tahoe, the problem we run into is that the primary productivity was only measured a few times in Emerald Bay, 1967 through 1971 sporadically. And that was really the time frame when Mysis were becoming established. And then again, there was one season, a summer season in 1978, when Emerald Bay primary productivity was measured. Now it's important to point out that during all of those measurements, Emerald Bay's primary productivity was higher than Tahoe. But since that time, Tahoe has experienced a fourfold increase in primary production. So it's generally gone from around 60 milligrams of carbon per meter squared up to 240, 250 milligrams of carbon per meter squared, a dramatic change in Tahoe itself. So what we really need to get a handle on this answer of how great an effect would Daphnia have on Tahoe, we need to have some contemporary data on primary production in Emerald Bay, so we can really kind of look at the differences between what Emerald Bay is now and what Tahoe is now, rather than relying on data from the early 70s. Well, there's been a lot of focus in Tahoe on the lower portion of the food web, but there are some questions about what would happen if you brought back Daphnia and reduced Mysis on the upper food web, on the fish response. And I want to make note that the following slides are based on previous research, recently acquired data during our 2011 to 2016 work in Emerald Bay, and then putting those together to create some hypotheses. So these next connections, they really need some more focused work before we can have definitive answers. But I'm going to talk first about the Mysis and lake trout. So we would expect that lake trout would be moderately negatively impacted by a reduction in the Mysis population. There was some work done by Dave Beauchamp in 1994 that showed that lake trout feed heavily on Mysis shrimp. And any anglers that are out there that are listening to the presentation, they obviously know this, because when you catch lake trout and they open the stomachs, they see a lot of shrimp in there. But what's more important actually is that from the study was that young lake trout can grow faster with Mysis because they have an abundant prey base down at depth where they live. And the prey is the right size for them to consume. So what Dave Beauchamp found was that the young year classes of lake trout grow faster, and you end up producing a greater percentage of your lake trout population that is capable of eating fish. Now, nobody should really worry if we were to reduce the Mysis population in Emerald Bay, your lake trout, or sorry, in Tahoe, your lake trout are not going away. They lived in Tahoe and did just fine for about 100 years before Mysis were ever introduced. So what about Daphnia coming back and the Kokanee population? We would expect that Kokanee would benefit in Tahoe from reduced Mysis population and a return of Daphnia. Kokanee size decreased when Daphnia disappeared after 1971. And the graphic on the bottom there actually shows the mean length of Kokanee returning to Taylor Creek after 1971. The California state record Kokanee was caught in 1973, just under 5 pounds. And since that time, that was when it was like the last fish that was able to feed on Daphnia during its life. And since that time, the Kokanee have averaged about 10 to 14 inches and around 1 pound, maybe slightly over. And if you've been to Taylor Creek and looked at the spawning grounds, you have a good idea of the size of the fish. In the absence of Daphnia, Kokanee diet switched from Daphnia over to copepods, specifically Dioptimus, which is our native bright red copepod out in Tahoe. But things changed in 2013. Suddenly a new California state record Kokanee was caught in Lake Tahoe, and it was over 5 pounds. And it was pretty interesting when this happened, listening to the anglers and seeing some of the news reports about it. People were speculating that this fish had some genetic differences maybe, or it was potentially maybe a 6-year-old fish that didn't spawn as they normally do at 3+ years old. But this is when we were doing our study in Emerald Bay, and we knew that there was a very large Daphnia population in Emerald Bay with the absence of Mysis. And so we speculated that the kokanee that spent their life in Emerald Bay, the 3+ years, feeding on a diet of Daphnia, would have a huge advantage over the Tahoe fish that were feeding on Diaptomus. So we went and collected some fish out of a spawning run that happened in Eagle Creek that enters into Emerald Bay. And on the left panel, the top fish and the bottom fish, we speculate were fish that grew up their entire life in Emerald Bay. And the other two fish in the center were Tahoe fish that migrated into Emerald Bay looking for spawning opportunities. So you can see a dramatic difference in the size there. And when we looked at the spawning run, about 1 in every 1,000 fish rivaled that state record that was caught off of South Shore. So during this time, we also collected some stomachs from fishing guides that were specifically fishing for kokanee in Tahoe and in Emerald Bay. And in the right picture, what you see on the left is a Lake Tahoe stomach, and it is bright red because that fish had been feeding on Diaptomus, the copepods in Tahoe. And the right stomach in the jar is virtually all Daphnia, and that came from Emerald Bay. So there was a very dramatic difference in the feeding in the two systems, and a very dramatic difference in the size of the fish resulting from that. But that's enough talk about introduced species. Lake trout and kokanee are both introduced species. How would Tahoe's native fish respond? And we suspect that Tahoe's native minnows would benefit from a return of Daphnia. Some work by Gary Thiede in 1997, he repeated studies that were done before Mysis introduction, or certainly before Mysis establishment in Tahoe. And he found that there was a 10-fold decrease in the native minnow population from the 1960s to the 1990s. And he attributed this decline to an increase in predation by lake trout. If you remember, Dave Beauchamp found that young lake trout were growing faster and could start eating minnows at a younger age. So a greater portion of the population was feeding on fish. That brought about a decrease in the minnows, but then also the loss of the minnow prey base, essentially losing the Daphnia from Tahoe, is what he attributed the declines to. So a decrease in Mysis and a return of Daphnia would be expected to decrease predation pressure on native minnows and increase the native minnow prey base. Well, what about Lahontan cutthroat trout? Kokanee salmon have been used on projects as a surrogate for LCT on how they behave and would perform in Tahoe. It's not a perfect fit because kokanee are pelagic feeders, whereas Lahontan cutthroat derive from the nearshore. So a better surrogate for how LCT might do would be the native minnows, maybe in combo with kokanee. And since we've seen that both kokanee and native minnows would likely benefit from a return of Daphnia, it's fairly safe to say that Lahontan cutthroat trout would also benefit, and it would likely improve their growth rates for reintroductions of cutthroat trout. Now, this isn't a big leap because what we're really talking about when we step back and look at the big picture is restoring native components to the Tahoe food web. And we would expect that native fish would respond positively to the native component, Daphnia, basically, of the food web. All right, well, I'm going to wrap up my talk there. And with a little luck here, I am going to answer some of these questions that have come in. So I have a question of, do any fish get trapped in the Mysis net? And I'm going to expand this to talk about bycatch of trawling. Bycatch being anything that is caught beyond your intended species. So the short answer is yes, there is bycatch. What we found during our trawling was that the native zooplankton are very small and go right through the mesh. So we don't harvest Daphnia when we're trying to harvest Mysis shrimp. But we did catch a few fish. And what we caught were juvenile kokanee and a few native minnows. And the key to this is that we really caught very few. When you target the Mysis, they're below the thermocline because they like that cold water. So when you get your trawl down to that depth, all of the other fish tend to either be above or below that. The lake trout were deep, and most of the kokanee, the juvenile kokanee, the native minnows are all right at or above the thermocline. So we had some bycatch, but it was very small. We also, if you look at the Lake Okanagan work, that was something they were very concerned about because they are harvesting Mysis to try and promote kokanee. And so they didn't want to be catching kokanee while they were harvesting the shrimp. And the reason kokanee were a big issue is because they are pelagic. They're out in the same zone where you're pulling your nets. They're not near shore. But they also at Lake Okanagan found very, very little bycatch, very few kokanee in their trawling efforts. Let me see what I can answer here. Is there any food competition between native kokanee salmon and native Lahontan cutthroat? Could removing Mysis exert more competitive pressure on Lahontan cutthroat? Interesting. It's something that I would be speculating a fair amount to get to that detail in that answering that question, because we really need to do more work on that. There was some recent work on how much feeding kokanee do on mysids, and it does become a fairly decent part of the kokanee diet in the last year of their life, in year 3. But that is in the absence of Daphnia. So if we had Daphnia, I think the kokanee would be fine eating that. The cutthroat trout are probably going to be eating both Daphnia and other things like native minnows around the shoreline. They really, spatially, they're really kind of separate areas, with the cutthroat trout being more benthic and near shore, and the kokanee being more pelagic. Here's a quick one in your slide about the trawl net modification. The picture on the back wall had a bathymetric map. In the background is that map data publicly available. There are bathymetric maps available of Lake Tahoe. They were produced by the USGS, and you can either find them through USGS websites, or you're welcome to contact us and we can direct you to those. I don't have a website for it right now. Also, if you're out on the lake and you are a boater looking for any kind of bathymetric imaging, a website called Navionics is outstanding for Tahoe, and you can use that to navigate over the bottom. It gives you depth contours throughout the bottom. Can you please explain the units on Mysis individuals? Why is it Mysis per square meter as opposed to volumetric cubic meters? Yeah, this is a confusing thing with the way people deal with Mysis and zooplankton. Zooplankton are typically measured volumetrically, as in liter or cubic meter, whereas Mysis are per square meter. The reason they do that is that Zooplankton are essentially obligate pelagic living species. They're out in the open water, in the midwater. And so a volumetric measure makes a lot of sense. Because the Mysis make their migration all the way down to the bottom when possible, it's always been viewed as more of a benthic organism. So how many Mysis would cover 1 square meter of bottom? And that's kind of the history on why you do aerial measurements for Mysis versus volumetric for zooplankton. But it does get very confusing when you're trying to equate those. What happens to the particles that the Daphnia ingest? So the Daphnia are feeding on fine particles, basically clay particles, inorganic particles, and also cyclotella or small algal cells. And what they do is they bring these into their gut through their mouth, and they digest what they can, and they package the rest into a fecal pellet that is much larger than the original particles that they consumed. So being a larger particle, their fecal pellets drop out of the water column and go down, sink down, and become part of the sediment relatively rapidly. Let's see. I believe at the height of LCT fishing, we were catching 250,000 pounds of LCT out of Tahoe per year. Do you happen to know how much all fishing is taken from Tahoe currently? I do not. I had heard a number of 100,000 pounds of cutthroat trout being removed. And this is always, it's an interesting question, because it's something that I've always kind of wondered about, is as our primary productivity went up in Lake Tahoe, that's the base of the food web. And I would expect that things above that would have benefited, and you would have a lot more fish in your system if you had a more productive system. But we don't really seem to see that. And I think the primary reason is that we measure our fish catch now primarily in non-natives as opposed to natives. So it's lake trout and kokanee and rainbow and brown. And they really weren't adapted to a Lake Tahoe system. So my guess is that we are seeing lower productivity at the top of the food chain, even though we have greater productivity at the bottom. And it's probably inefficiencies in the species that are actually there. All right, I am going to wrap up the questions there. If I didn't get to your question, we are going to do a frequently asked questions page, and we'll put out a link or make sure you get access to that so you can see written answers to questions that have come up. And thank you very much for attending today. I appreciate it, and have a great day.